Today, I present two topics. Topic 1, Section 3.5, two well-known limits. Topic 2, more examples about derivative formulas. Topic 1, these two limits are well known to mathematicians. By tables, it is easy to see that when x approaches 0, sine of x and cosine of x minus 1 both approach 0. Essentially, the first limit says that sine of x and x approach 0 at the same speed because their ratio approaches 1. Essentially, the second limit says that cosine of x minus 1 approaches 0 faster than x approaches 0 because their ratio approaches 0. By tables, we can verify these two limits. This table verifies the first limit. In this table, I let x approach 0 by taking on these points. Using my calculator, I compute the values of sine at these points. We can see that sine of x also approaches 0 and at the same speed with x. As a result, sine of x over x approaches 1. This table is for the second limit. In this table, I let x approach 0 by taking on these points. The second column is the values of cosine of x minus 1 at these points. The second column shows that cosine of x minus 1 also approaches 0 and is faster than x approaches 0. As a result, cosine of x minus 1 over x approaches 0. These two limits have been used to obtain these two formulas. Derivative of sine is cosine. Derivative of cosine is negative sine. Let me show you how to get this formula from these two limits. By the definition of derivative, derivative of sine is this limit. To find this limit, we can try direct substitution. Plug in 0 in h, then we have sine of x minus sine of x over 0. Sine of x minus sine of x is 0. So we have 0 over 0. We cannot tell this limit. To find this limit, we need to simplify the function. We expand sine of x plus h by this trigonometric formula. Then we have this equation. Now, move the third term in the middle position. Then we have this equation. In the first two terms, take sine of x out. Then we have this equation. Now, split this quotient into a sum of two smaller quotients. For this limit, we apply these two well-known limits. As h approaches 0, cosine of h minus 1 over h will approach 0 by this limit. Psi of h over h will approach 1 by this limit. So the whole thing will approach psi of x times 0 plus cosine of x times 1. Psi of 0 times 0 is 0. Cosine of x times 1 is cosine. So this is cosine. Therefore, derivative of sine is cosine. Here are some examples about how to use the two value limits to evaluate some other limits. Recall that the first value limit essentially says that as x approaches 0, psi of x and x, they approach 0 at the same speed. The second value limit essentially says that as x approaches 0, cosine of x minus 1 approaches 0 faster than x approaches 0. Example 1. Use these two limits to evaluate the following limits. Part A, as x approaches 0, this function will approach some number. We need to determine that number. The number is this limit. About the function in this limit, the argument of sine is 3x. The denominator is just x. They are different. So we write this function as this function. Move the number 3 outside the limit, then we have this equation. Now, as x approaches 0, 3x approaches 0, and sine of 3x approaches 0. But according to this limit, sine of 3x and 3x, they approach 0 at the same speed. Therefore, this quotient will approach 1. So the limit is 3 times 1. It is 3. So this limit is 3. To find the limit in part B, first, write tangent of 4x as sine of 4x over cosine of 4x. About cosine of 4x, as x approaches 0, cosine of 4x approaches 1. So we can replace cosine of 4x by 1 without changing the value of the limit. So we have this equation. Now, to find this limit, we write the function as this function. As x approaches 0, 3x approaches 0. Sine of 3x approaches 0. But by this limit, sine of 3x and 3x, they approach 0 at the same speed. So this quotient approaches 1. So we can replace this quotient by 1 without changing the value of the limit. So we have this equation. Now, to find this limit, we write the function as this function. As x approaches 0, 4x approaches 0. Sine of 4x approaches 0. But 4x psi of 4x, they approach 0 at the same speed. So this quotient will approach 1. Therefore, this limit is 1 times 3/4. So the limit is 3/4. Part C. To find the limit in part C, first, factor x squared minus 4 as x minus 2 times x plus 2. Then write this fraction as this fraction times this fraction. As x approaches 2, x minus 2 approaches 0. And psi of x minus 2 approaches 0. But they approach 0 at the same speed, so this quotient, this fraction, approaches 1. 1 over x plus 2, as x approaches 2, approaches 1/4. Therefore, this limit is 1 times 1/4. It is 1/4. Part D. To find the limit in part D, first, factor cosine square minus 1 as cosine minus 1 times cosine plus 1. Then write this fraction as this fraction times cosine plus 1. As x approaches 0, cosine of x plus 1 approaches 2. Cosine x minus 1 over x, this fraction approaches 0 according to the second limit here. So this limit is 0 times 2. It is 0. So this limit is 0. Now, topic 2. More examples about derivative formulas. Example 1. Consider this function. This function is defined piece by piece. The a here is some constant, some number. Part A. Determine the value of a so that the derivative of the function at point 0 exists. Part B. With the value of a determined in part A, is the function differentiable at any value of x? Differentiable means derivative is computable. Derivative exists. This example doesn't require me to plot the graph of the function. But I still plot the graph here to help myself answer the questions. The graph of a times x, a is some number. The graph of a times x is a line. The line passes through the origin. Because I don't know what a is, here I arbitrarily draw a line through the origin to represent the graph of this function. The graph of x squared minus 3x is a parabola. The graph of a polynomial of degree 2 is always a parabola. When x is 0, 0 to 0 squared minus 3 times 0 is 0. So this parabola passes through the origin. When x is 3 3 squared minus 3 times 3 is 0. This parabola also passes through this point. Because the leading coefficient is positive, this parabola is open upward. So this curve is the graph of this polynomial. Now, I answer these two questions. About part A, I have two solutions. In solution 1, I use the definition of derivative to answer the question. By this formula, derivative of g at point 0 is this limit. This limit is a both-sided limit. That means that x can approach 0 from the left side of the point 0, can approach 0 from the right side of the point 0, can approach 0 by jumping around 0, can approach 0 in any other way. No matter how x approaches 0, this quotient should approach the same number. Otherwise, we say that this limit doesn't exist. In the case, derivative at 0 doesn't exist. Because the function is defined differently from the left and from the right at the point 0. On the left side of the point 0, the function is a times x. On the right side, the function is x squared minus 3x. They are different. Because the function is different from the left and from the right at the point 0, we compare one-sided limits instead of computing these both-sided limits. Namely, we compare left-hand side limit and right-hand side limit at the point 0. This is the left-hand side limit at the point 0. In this limit, x approaches 0 from the left side. X approaches 0 from the left side. In this approaching process, x is less than 0. When x is less than 0, the function is a times x. So we have this equation. Now, cancel x from this limit, then we have this equation. A is a constant, so this limit is a. Therefore, the left-hand side limit at the point 0 is a. Right-hand side limit. X approaches 0 from the right side. X approaches 0 from the right side. In this approaching process, x is greater than 0. When x is greater than 0, the function is this. So we have this equation. On the top, I factor x out, then we have this equation. Cancel x, then we have this equation. To find this limit, direct substitution. Plug in 0 in x, then this limit is 0 minus 3. It is negative 3. So the right-hand side limit at the point 0 is negative 3. Now, in order for this both-sided limit existing, left-hand side limit and right-hand side limit, they should be equal. Therefore, a must be negative 3. So the answer to part A is, when a is negative 3, the derivative at 0 exists. Here is a second solution to part A. In this solution, I compute the derivative of this function and also compute the derivative of this function. The derivative of a times x is a. Derivative of x squared minus 3x is 2x minus 3. A derivative is the slope of the tangent line at the point x. Now, plug in 0 in this derivative, we get a. Plug in 0 in this derivative, we get -3. That is, the slope of the tangent line to this curve at the point 0 is a. And the slope of the tangent line to this curve at the point 0 is -3. Recall that when a graph has a corner at some point, at that point, the function has no derivative. So in order that the graph of the function g has no corner at the point 0, these two slopes should match. That is, a should be -3. When the slope of this line at the point 0 and the slope of this parabola at the point 0, these two slopes are equal, then this graph has no corner at the point 0, and therefore derivative exists there. Now, part B. With the value of a determined in part A, is the function g differentiable for all the values of x. From part A, we saw that when a is -3, g is differentiable at the point 0. At a point x is less than 0, the function is a times x. A now is -3. This function is differentiable. The derivative of the function is -3. At a point x is greater than 0, the function g is x squared minus 3x. This function is also differentiable. The derivative is 2x minus 3. So we conclude that the function g is differentiable everywhere if a is -3. Example 2. Find an equation of the tangent line to the graph of this function at this point. This point is a point on the graph of the function. To help myself answer the question, I arbitrarily draw a curve and suppose this curve is the graph of this function. Suppose this point is here on the graph of the function. At this point, there is a tangent line. We need to write down the equation of this tangent line. About this tangent line, we know one point on it. So what we need is the slope of the tangent line. To find the slope of the tangent line, we compute the derivative on the function. The function is a quotient. So by the quotient formula, we have this equation. Now, derivative of ex is ex. Derivative of 1 plus x squared is 0 plus 2x. So we have this equation. Simplify the numerator a little bit, then we have this equation. This is the derivative of the function, and also it is the slope of the tangent line to the graph of the function at the point x. Now we can tell the slope of this tangent line. Plug in 1 in x here. Then the slope is 0. It turns out that this tangent line is horizontal. Now we have the slope of the tangent line and 1 point on the tangent line. By the point slope formula, the equation of the tangent line is y minus y1. y1 is the y coordinate of this point. It's equal to slope. Slope is 0 times parentheses x minus x1. x1 is 1. Simplify this equation, then this is the answer to this example. Example 3. If function f is square root of x times function g, where function g f4 is 2, the derivative of g f4 is 3. Find the derivative of function f f4. To find the derivative of f at the point 4, we first compute the derivative of f at the point x. Because all the 10 formulas are about derivatives at the point x. After we get the derivative of the function f at x, plug in 4 in x to get the derivative of f at the point 4. The function f is a product. Square root of x times g. So we can apply the product rule to this derivative. Then we have this equation. The derivative of square root of x is 1 over 2 times square root of x. The detail is here. So this is the derivative of function f at the point x. Now, plug in the number 4 in the x here. Then derivative of function f f4 is this. By the given, g of 4 is 2. Derivative of g f4 is 3. Then we have this equation. This number is 13 over 2.